So those who are listening in on the live stream, I'm sorry I got a bit late. I'm just starting up the lecture. Just give me a few more minutes. Yes, it's me. Okay. Week 10, lecture slides, save link as. Should come up now. So why can't I write? Oh, I can. Hallelujah. Okay, so I really apologize for getting late today. So it was beyond my control. Or probably it was if I started rather at 7 at 6:40. All right, so we are going to talk about linear programming. So we've been discussing a few topics, and the idea of this unit was to give you an introductory aspects of various real-world algorithms and data structures, and linear programming is surely one among them. And there's some data structures that are easy, some that are difficult, but I can assure you all of them are real world. Unless one's opinion is that a data structure is import a library in Python and use it. Well, that's not why we do computer science. Edgar Dijkstra famously said that computer science is not about computers, just as astronomy is not about telescopes. So using a computer with an input is not what we do these courses for, but to understand under the hood. Okay, so linear programming is one such thing. It really arose, like many great innovations arise for completely wrong reasons. It arose around World War II. Military logistics was the main reason why you would want to why this field of mathematical programming started. Linear programming is a branch of mathematical programming. And then the idea would be that how do you solve combinatorial optimization problems of a specific kind optimally under certain resource constraints. And there was this famous paper, a couple of papers that he wrote in quick succession that became landmarks in what later on evolved as initially operations research, And then later on, when computer science grew in its own, computer science in the 70s was still in mathematics departments, and then deans realized that there's a branch of science by itself, and then they started having departments of computer science, and it became combinatorial optimizations once the algorithmics, once the complexity analysis all started tying in. So the method that we'll be solving is called a simplex method. It was proposed in around 1949, and sometimes it's very hard to know why is an algorithm, what's the fuss about an algorithm. Perhaps, especially when you're starting off thinking about it, you'd want to take some faith in what some giants think about the same thing. And the quote by Richard Karp, Rabin Karp's algorithm, Karp did phenomenal analysis in computational theory. So Karp's views are sort of reflective of the merit that giants gave to at least the contribution, the very importance of the contribution in 20th century mathematical programming. So it's one of the, perhaps the most important algorithms developed in 20th century. Importance is fairly a subjective term. People find it important for various reasons, but let that be. The fact that you have renowned figures talking about the importance is a good enough motivation for us to at least understand the initial aspects of simplex algorithm. Yeah? Now, for this, I'm going to use a toy problem. The problem is fairly simply defined. So let's assume that there is a manufacturer who wants to manufacture two products. We'll call them A and B. And to manufacture each of these products, you require two resources, resource 1 and resource 2. To make 1 unit of product A, you need 1 unit of the resource R1 and 3 units of resource R2. Similarly, to make 1 unit of B, you require 1 unit of resource R1 and 2 units of R2. Now, it turns out that it's the first few bullet points, the first 4 bullet points only talk about what it takes to make a product, a couple of products A and B. It doesn't really tell you what are the constraints that you have. So there are some resource constraints. So the manufacturer cannot buy resources willy-nilly. So he's going to, the manufacturer has only 5 units of R1 at her disposal, their disposal, and 12 units of R2 on the other hand, that's available to make those products. But he does know that every product that he makes of A, every product that the manufacturer makes of A gets you $6 of profit, and it will be $5 of profit if it's B. The problem is fairly simple, isn't it? So there are some statements of what it takes to make products. The manufacturer knows what the objective function is. We'll see what that means. And then he or she has some resource constraints. The decision the manufacturer has to make is how many products of A and B should the manufacturer make to produce, to maximize the profit. Now, the formalism in algebra is fairly something very simple. You would have written this, you have seen some form of this in your high school, if you're doing some aspects of mathematics. So you take that, okay, let's assume the number of units of product A to be, we'll call them X, and number of units of product B to be produced is Y. So these are, X and Y are variables that the manufacturer has to make a decision on. So they are decision variables. They are something that, given the constraint, the manufacturer needs to make a decision how many of A and how many of B, and we're calling them how many of A as X and how many of B as Y. Now, the objective function is very clear. If the manufacturer makes X units of A and Y units of B, the objective function is 6X plus 5Y. There's nothing more than this, right? And then it turns out that for each unit of A requires 1 unit of R1 and requires 1 unit, or for each unit of B requires 1 unit of R1. So essentially, there is a constraint on how many resources of R1 available. There are only 5 units of R1 available. If you're making X units of A and Y units of B, and X units takes 1 unit of R1 and Y units each take 1 unit of R1, so then X plus Y is less than or equal to 5, because that's the resource constraint. To make X, to make product A or product B requires some units of R1, and that 1 time X plus 1 time Y is less than or equal to 5 is stating the resource constraint, right? So you cannot have more than that. Is that clear? Now, similarly, it takes 3 units of R2 to make A and 2 units of R2 to make B, and there are only 12 units of R2, so 3x plus 2y is less than or equal to 12. So in all this, there is an implicit constraint that the number of units of A and B are non-negative, greater than or equal to 0. All right, so obviously a sensible manufacturer wants to maximize the profit given the resource constraint. So the objective function Z equals 6x plus 5y has to be maximized. So that's a classic scenario where you have some number of decision variables, how many, in this specific problem, how many units of A and B to make, some objective function, in this case it is Z equals 6x plus 5y, and some constraints, and the constraints basically are of that form. Okay? Now I want you to focus that all constraints are linear. There are no powers of 2 or no exponential terms in this thing. They are linear constraints. X plus y less than or equal to 5, 3x plus 2y less than or equal to 12, and x comma y greater than or equal to 0. Okay? So these are, you have to now make decisions using the objective function subject to the constraints. Is that clear? Okay. Now, if you have to make these choices, the program, the reason why it's called linear programming is because the objective function is linear, your constraints are linear, and they are, of course, there's a non-negativity constraint on the decision, on all variables really, but on decision variables specifically. So if you look at this statement here, what linear programming is trying to solve is that if you have a optimization problem that follows this form, then you could potentially, it'll give you a way to have a solution, a crack at the solution towards it. Okay? Let's see how, but let's generalize this a bit more. I mean, but although the example we've used will persist all through the lecture, but generalization is important. So if you look at the maximization, you need not have 2 decision variables. You could have n decision variables, that x1, x2, x3 to xn are n decision variables. So z equals some coefficient c1 times x1 plus coefficient of c2 times x2 all the way to cn times xn. That needs to be maximized subject to the constraint. Again, your linear constraints x1, x2, x3 are all linear terms in each constraint, each row of the constraint. The a11, a12, a1n, a21, a22, a2n, all the way, the coefficients of everything on the left-hand side is like a matrix of coefficients. Now you have the decision variables x1, x2, xn is less than or equal to b1, b2, all the way to bm. Yeah. So what you can do is maybe write it. I'll just go to the board here for those who have some linear algebra in their arsenal. You don't have to worry about linear algebra beyond the most basic ones you have learned in your prerequisite math in high school. But so if you have a matrix A, which is A11, A12, A1n, A21, A22, all the way to A2n, AN1, AN2, ANN times x1, x2, dot, 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 xn is less than or equal to, oh, sorry, I think they are not a fully determined system. It's some generalized system. So I'll call, if there are only m constraints, there would be m rows of that equation. So I'm just not making it a square matrix, less than or equal to B1, B2, B. So that's going to be Bn, right? So that's basically their n terms. They're not, it's a rectangular system, m cross n. So this is going to be an m cross n matrix. This is going to be an n cross 1 matrix. So it's going to be m cross 1. Okay, so that's basically how that system that we are talking about, so system of linear inequalities can be captured in linear algebra quite efficiently, in a shorthand. Linear algebra is nothing but shorthand to a system. So A x less than or equal to B. Okay, so that's basically a vector form, a representation that you could actually write that as. So, but this is a standard form where you want to maximize something. There are constraints, everything is less than or equal to constraint, and then there's a non-negativity constraint at the very end. So this standard form is called a canonical form of linear programming. Now, I just want to tell you straight away that the whole idea is that when you get problems that are not in the standard form, you don't have to worry about it for this lecture, but in general, very simple transformation of this problem statement gets you to the standard form, and you have a way to solve it using simplex. Okay, so that's what people usually do. If you don't have let's say you had a greater than or equal to constraint, or if you have a strict equality constraint, what do? You kind of just transform it into a form which is equivalent to a standard form. Now, I'm going to give you sort of first part. I'll be focusing on the intuition of why we need to have a good algorithm. For that, I'm going to talk about some insights that we get about this problem by graphing it. Now, graphing something, because they're linear equations, linear inequalities, I can graph it. Graphing is useless if you have the dimensions greater than or equal to 3, or greater than 3 maybe. 3 dimensions are still possible, but really because there are only 2 decision variables, it's a 2-dimensional problem, so I can graph it. So if I graphed the constraints, x plus y is less than or equal to 5, so that would be the red line. 3x plus 2y is less than or equal to 12, it would be the blue line. Okay? Now, x and y greater than or equal to 0 is the first quadrant of the xy plane. Yeah? So if you see, there's a boundary that you have. The boundary essentially goes from there all the way. So that's what's shaded. Can you see the shaded part in the on the screen, right? So, okay, the shaded part is basically the boundary of what is it a boundary of? It's the boundary of feasible solutions for x and y. For x and y to be feasible, subject to this constraint, you have to explore a solution in that boundary, in that region. Okay? Now, what are the insights that you get? That's a feasible region is defined by those constraints. That's the shaded part. This will be less obvious. Take it as a statement of fact that if you have a linear program in a standard form, it will basically be I'm just distracted by the noise outside. It will basically be a convex polygon in this case, because 2D, if you generalize it, it's going to be convex polyhedron. Now, what does convex mean? There's a strict mathematical definition, but if you want to understand what convex means, take any pair of points defined by that region. So this basically, it's a polygon in this case, defining that grayed region. Take any pair of points, draw a line, it will be at the boundary or within that region. You never have a line going out of it. So for instance, what is not a convex polygon would be like that. If I drew a line between a certain set of points, then you would basically have, so this line here is not within the region that it defines. So convex polygons are those where you can never have a pair of lines between vertices of that defining that polygon that is not subsumed within the region that it defines. Now, there is a reason why this is important. Now, what did we say? What did we say the objective function was? Z equals 6x plus 5y for this problem. So what is z equals 6x plus 5y? Z is some value that you have to decide. It's a constant that you would eventually have. But if z were some constant, 6x plus 5y equals to some constant is a line, isn't it? Now, if you took a line and the slope of that line is defined not by the value of z, it's basically for any different value of z, you get basically different intercept, but the slope is exactly the same. If you think about the line, 6x plus 5y equals 10, and 6x plus 5y equals 20 or 27 or something like that, they all will have parallel lines. They define a system of parallel lines. Now, think about this line sweeping in that xy plane, the first corner point that it touches, because all the vertices are outside, they're convex, it will have to hit at least one corner point when you're sweeping, when the objective function line is sweeping towards that polygon. At some point, the moment it touches, the first point it touches while it enters the convex polygon is basically, so if I had, I can't seem to, I have to somehow swap the screens because out here I'm seeing this. Maybe if I, how do I toggle this back to all displays? Maybe all displays? Yeah, there you go. Good, thanks. So if you have a system of parallel lines, and let's assume that's a slope for 6x plus 5y equals some constant c or z, we'll call the constant z. At some point, when you sweep that objective function line, it's going to hit one of the corner points. So what next two insights are essentially telling you why you will have always a corner point that dominates, but before that, if you have any point in the convex polytope, let's call it AB, the idea would be that if I increased, if x equals A and y equals B, if I increased or decreased depending on my objective function coefficient, the coefficients need not always be positive, they can be negative coefficients as well, but if you essentially have increase or decrease, you can eventually go this way or this way on one dimension and this way on the other dimension, which always will give you a higher evaluation. Any one direction, depending on the choice, would always give you a higher evaluation for any fixed point AB inside the region. You can see why that's the case, that everything in the boundary, I'm going to draw the boundary here, that's the boundary of that region. All the points on the boundary of that region, there will be at least one point on that boundary that dominates any point within the region, because all I can do is for any fixed point there, depending on the coefficient is positive, go increase the value in the x dimension if the coefficient of x is positive. And then obviously, whatever you evaluate A as B, A plus x will give you a greater value if the coefficient is positive. If it's negative, you have to decrease it. So depending on which direction you go, you're going to hit the boundary at some point. So there's always going to be some point on the boundary that dominates it. So what do we say? We don't have to worry about all the points inside. You only have to put the focus on the points defining the boundary to evaluate the optimization of this problem. Now, it gets even better. You don't even have to worry about all the points on the boundary. You only have to worry about the corner points defining the feasible region. Now, y is the reason I said if you have objective function z equals 6x plus 5y, it defines a family of parallel lines. Essentially, what you're trying to say is if it's a convex polygon, one of the vertices would be protruding outside. They're not concave, it'll be convex, it'll be outside. So before you see anything else, you'll be seeing at least one corner point. And I said at least one, not exactly one, because sometimes you can have a boundary that is parallel to the objective function. So you're essentially going to be flat, you're going to meet an edge before you see, an edge is defined by two corner points, so you essentially have two feasible solutions anyway. Infinitely many, but at least two. You just need one, really, when you're optimizing for something, okay? So with that insight, now let's see if we can get some more insights about the nature, the complexity of the problem when we are exploring this in some naive way, because clearly all I have to then do is explore the solutions in the corners. For how many ever corners you get, I'm just going to substitute the value. If I have to find the maximum over all possible corner points, then I have a method, a dumb method at least, to sort of select the optimal, right? So now if I were doing this, let's come back to this thinking in some algebraic way. So let's take the first constraint, x plus y less than or equal to phi. Now let's use some notion of what's called a slack variable. So how do I change that inequality to an equality? So if I add x and y, I'm going to evaluate a number that is less than or equal to phi. For me to make it strictly equal to 5, then I need to introduce a variable, and I'll call the variable s. It's a slack variable. How much slack do I have before I reach equality? Basically, that's why it's a slack variable. So if I have x plus y less than or equal to phi, so if I add this number, it could have, if the number could have, so remember x and y are greater than or equal to 0, x and y could add up to 0, or add up to 1, or add up to 2, or add up to 3, or add up to 4, or some number in between. So whatever, if it adds up to 0, I can include a slack variable s and make it 5, because if x and y adds up to 0, then slack would be 5. X and y add up to 1, slack would be 4, and so on. Similarly, if I have another constraint 3x plus 2y less than or equal to 12, I can add another slack variable t and make it equal to. So s is greater than or equal to 0 and t is greater than or equal to 0. There's a non-negativity constraint there as well in the standard form. So an objective function is simply 6x plus 5y. Remember, objective function should be a function of all variables. So, but I have this s and t, there's a new variable, so z equals 6x plus 5y, but I can easily say plus 0s plus 0t. So essentially, I have introduced variables, but my objective function doesn't care about those variables by putting the coefficient of 0 against it. Okay, so if that's all clear, so if you look at the transformation of inequalities to equalities, this is important. Maximize 6x plus 5y, so that's maximize this. So I want to maximize this. Now subject to what constraints? So subject to the constraint 1 times x plus 1 times y plus 1 times s plus 0 times t. I'm just going to make it complete, equals phi, and then 3x plus 2y plus 0 times s plus 1 times t equals 12. Can you see? And then I have x, y, s, t all greater than or equal to 0. So if I have a statement of that kind, how do I go about solving it? How do I go about solving it? Okay, now I have two equations. How many unknowns do I have? 4 unknowns. 2 equations and 4 unknowns. Can I solve it? It's an underdetermined system, isn't it? You need to have, if you have, in linear algebra, you have a notion of rank of a matrix, right? So you need a system with a full rank for you to be able to solve this. If you have basically things defined in a vector subspace that is less than what you're solving, then less than n in this case, n decision variable, n equals 2, you can't. So you have 4 variables, or if you want to hand wave it without mathematics, you have 4 variables and 2 equations, so you can't solve it. How do I solve it? By fixing 2 values for 2. Find 2 values, fix some values, and can I fix that values in some sensible way? And it's very easy to what to choose to fix those values, right? So if I have 4 values, there are 4 variables. If I have to fix 2, there are 4 choose 2 ways in which I can fix. 4 choose 2 is 6 ways, isn't it? 4 times 3 divided by 2. 6 ways I can fix to solve for the other 2. Now, why do I care about fixing these? By the way, this is not simplex, this is intuiting. So I can fix at this corner, or 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 this corner. So think about what these 6 possibilities are. 6 possibilities are talking about 4 of the corner points of the feasible region, plus 2 of them that are infeasible outside that region. In fact, now how do I fix so that I'm evaluating these in a dumb way? Well, look at what happens out here. The variables here are x, y, and s and t. Out here, x and y are 0. So I must say that let me just go to all displays. Let me change that thing. Okay, so I can scribble here as well. So if there is an s associated with, so s is associated with this, t is associated with this. So if you look at this point here, x is 0. What else is 0? So if you are at a corner point of a red line, the slack of s is 0, isn't it? S becomes 0. 0 out there. So there's still some slack with respect to t, but not with respect to s, so to speak. So, and then out here, y and sorry, actually this one is t, isn't it? So I forgot which one is which. Give me 1 second. I'll just write this carefully. So this is the first constraint, wasn't it? I can't remember the order in which we defined the constraints. X plus y plus s equals 5 was the first constraint. Okay, so that's the first constraint. So red is the first constraint, and blue is the second constraint. So you had s associated with the first constraint and t associated with the second constraint, correct? I think that was correct. So, so this out here, x and s are 0. Out here, y and t are 0. Out here, s and t are 0. Out here, x and t are 0. Okay, I think in various combinations, and out here, x and y are 0. Okay, and we'll see that in the next slide. Anyway, so if you fix pairs of points, x and y equals 0, that means it's x and y equals 0 implies the first one implies this point. The second one, x equals 0 and s equals 0, implies this point. So first, second, x equals 0 and t equals 0 defines, so that's going to be yeah, so 6, so that becomes that point, 3. And then, I don't know why it's jumping that way. Give me 1 second. Yeah. Then if I did the fourth point, you get that. That's the fourth point. The fifth one is, fourth point is this. Sorry, fourth point is this, fifth point is this, and sixth point is this. So essentially 6 possible ways in which you can define these points. Now, if you did this, you can fix it in a pair of points to 0 in this example, and then you can essentially say that if you evaluate, if you fix those points, x and y have specific values, isn't it? In the first point, when you fix x and y to 0, obviously objective function is 0. In the second, when you fix x and s to 0, objective function will be 6 times 0 plus 5 times y, which is 25. And so you have different evaluations of objective function for each of the x, y combinations that you could get, and you can choose the maximum. Now, I just want to give you a counterintuitive alert. In fact, this is very, very important, because otherwise you'll get confused. So there'll be a notion of non-basic variables in simplex, and then a notion of basic variables. Now, it's counterintuitive because for all practical purposes for this lecture, whenever I say non-basic variables, think about the variable that's fixed to 0. And whenever I say it's basic, it's variables that are free, not fixed. So non-basic variable means fixed to 0, specific value of the fixed only to 0, nothing else. The non-basic variables are fixed to 0. Basic variables are free. Whatever values you end up getting once you fix the other variables to 0 is what you would get. Now, there's a reason why we call this a basic variables and non-basic variables. For instance, in this form of the equation, you can see that 1, 0, 0, 1 is against the coefficient of s and t. You kind of have sort of a coordinate system that is being defined in terms of s, in terms of t. I mean, you can think of it to be a basis of these equations, and we'll see what that means in simplex a little later. But all you have to think about, I'll just go back, is non-basic variables here are those that are fixed, and basic variables that are free. Are you going to keep that in mind, everyone? Please keep that in mind while we listen to the lecture. So if you evaluate z, it turns out that you will evaluate z at all possible corner points, but couple of corner points are infeasible. Why are they infeasible? It's because they're outside the feasible region. Because you remember that you're evaluating points. I'll just go back a bit. You're evaluating points here and here which are not feasible. If you evaluate a point, objective function here and here, they are surely not feasible. So you can don't care about them. Now, if you did this method, you are in trouble, right? So why are you in trouble? I already said all these points are corner points. There's nothing more on the slide. So why do if you generalize this method, you're in trouble, because if you have n decision variables and m constraints, which is a rectangular system, then for each constraint you have a slack variable. So there will be m slack variables. The total number of variables would be the number of decision variables plus number of slack variables. That's n plus m. Now, out of which you have m equalities now once you introduce slack. So what do you have to do? You have to assign n out of n plus m to zeros. You have to fix them, make them non-basic. If you have only m equations, you can solve for a well-determined system with m variables and m constraints, but you have n plus m variables, so n of them have to be fixed to 0 to be able to solve for the other m, isn't it? So if you have to make n of them non-basic, you will have m basic variables to solve for. And if you kept doing this for all possible corner points in the general thing, you have n plus m. Choose n possible ways, because you're choosing n each time out of n plus m to fix to 0. to define a corner point, and then enumerating them is clearly has a factorial complexity associated with it. It's not a practical algorithm if you want to do this naively, right? And it's our luck will have it, Murphy's law, that we'll have to enumerate. There's nothing that tells us prematurely if we reach the optimal. We'll have to wait for all the possibilities to have been explored before we know that there is an optimality that has been reached. So this method is clearly not useful. So it grows factorially large, combinatorially large, evaluates infeasible solution. This is at best a exhaustive brute force method, and there's no method in the madness. It is always going to evaluate whatever common point entails. There's no progressively, you're not getting a better and better solution. The search is fairly random for the optimality. With that motivation, all this is to motivate you what this simplex method is, that, well, simplex method is a method to solve this problem in polynomial time in practice, and all practical problems it's going to be polynomial, pardon me. And then in worst case, it's actually a non-polynomial time algorithm, although there are provably polynomial solutions for a simplex problem, interior point methods. Every practical problem, the go-to solution is simplex because in practice it outperforms anything else. It does not ever evaluate infeasible solutions. It always explores progressively better solutions each time and tells you when the optima has been reached. The moment you reach an optima, it stops. Okay? Have you come across any algorithm that allows you to always progressively enumerate better and better solutions and then stop the moment you know you have reached the optimality? Anything that you can draw from your previous units? Quiz? Okay, if I ask you to look at all the algorithms you've done on graphs, anything that comes to your mind as you're solving some optimal problem, solving some optimality, and you're progressively exploring better and better solutions, and you stop. At some point you stop and you say, well, once I stop, it terminates at an optimal value. Do you remember any such algorithm? I'm pretty sure you've done one such. Network flows. Ford-Fulkerson. Have you done Ford-Fulkerson? Do you see how the min-cut max flow? In fact, you can write your min-cut max flow problem into a general linear programming form and solve it. Except that min-cut max flow is a specific problem, so you could have done it Ford-Fulkerson. The method that you would have thought would be a pseudo-polynomial time algorithm, which, so did you do a BFS so do you remember how you kind of had this graph residual formulation of your graph, and then you had to run a breadth first search to be able to find an augmenting path, and then suddenly you stop, and when the word augmenting is progressively better, right? So you're making, and then you stop and automatically you seem to solve two problems, a max flow and a min cut, and there's a min cut max flow theorem. In fact, there are a class of problem called dual simplex problems, because you're solving one problem in a dual way. So solving one has a dual that you solve. We'll see a variety of that in the next week lecture anyway, but all these things are interconnected. If you think about how the journey has been, they're subtle. Sometimes it seems, why am I doing this? But they're all connected in some ways. Yeah. So, and if to explore those fine connections makes you a better computer science scientist, basically. Okay. So and we're going to see how that's going to happen. We're going to do it in two forms. So one would be understanding form, theoretic. How do I understand what's happening to do a solution? So clearly I have to find a solution in the corner points, not ever explore infeasible solutions, and once I go to the optimality, I should stop. I should not even if the first point I enumerate is the optimal, I should be able to stop right then and there. Okay, so there's no more exploration needed, even if there are combinatorially many points that have to explore. Okay, so let's see how do you do this in terms of what's really happening in terms of the algebraic form of simplex. But algebraic form simplex gives you the intuition of what's really happening, but when you have to convert a program to it, you need a tabular form. Most students groan when we talk about tabular form, but it's not as difficult as it would be when you first think about it. But it's because it's such a crank turning exercise. If you understand the intuition that crank turning should fall in place. So tabular form, posh word French for that is tableau. The tableau form is crank turning. Real understanding will be algebraic, and I'll show you the relationships at the end, one-to-one, what is really happening at every step. Okay, so you will not be lost in connecting those two. Okay, let's start with the algebraic form. I'm using the form of the linear program where slack variables have been introduced and inequalities have become the equalities. Okay, I'm using the same problem, but we're going to treat them as equalities rather than inequalities by introducing a slack variable. So, method 1, start at a corner point where the decision variables are 0. So you have to solve for the optimality for a decision variable. Well, what better way to start than to say, okay, what if my variables are all 0, the lowest possible values. So what did I say the category that we said we're going to call anything fixed to 0 as non-basic variables. So the current non-basic variables are the decision variables x and y. That immediately gives you a solution for the basic variables. What are the other variables there? If x and y has been fixed to 0, the other variables are s and t, right? So obviously, can you see why s and t can be solved? Well, if I put x and y to be 0, s will be 5, x and y is 0 out here, t would be 12. So I've solved for s and t. Easy, right? So there's nothing more there in it. Now, that is where I've started in my journey for the optimality. Now remember that I might give you an intuition that when you were doing the brute force, the exhaustive method, you were exploring the corner points arbitrarily. Out here, you're not going to explore the common points arbitrarily. You start from the least possible value that you could take in this current form, x and y being 0. Then, there are only, in this problem, what are the corner points connected to this thing? So there's one corner point here in the feasible region and one corner point here in the feasible region. So I could potentially go in a connected path from here to here or from a connected path from here to here. Okay? The idea is to always go towards the optimal point as a connected path from the place that you started. Okay? Now, how do I make a decision whether I should go this way or that way? Or if you have multi-dimensions, there will be so many other ways in which you could go. Okay? This is only a two-dimensional way of thinking, and you always have to generalize it. I can only see things in my head in up to 3 dimensions, but anything more, you have to rely on mathematics, right? So that's what you need to do. Okay, so if you had this insight there, keep the insight that we are always going on a connected path, right? Always a connected path. So out here, what you need to do is what you have to do is you have those constraints. X and y are fixed to 0, non-basic. S and t are free. They can take whatever values one has once you fix x and y. Now, because s and t are free, they form a basis to define everything in this system. Now, let's view everything from the point of view of S and T. Now, how do you view everything in the point of view of S and T? Well, write an equation such that if I rearrange this thing, all basic variables are on the left-hand side, all free variables are on the left-hand side, in the constraints, in the objective function, and so we'll talk about the objective function a bit. For the constraints, all the basic variables are on the left-hand side, and all the fixed variables, non-basic variables, are on the right-hand side. Because x and y have been fixed, can you see that I've just rearranged the first equation here. If I rearrange this equation here, I get that. And if I rearrange that equation there, I get that. Now, all I am making sure is that the left-hand side is basic and right-hand side has non-basic terms. Now, more precisely, the coefficient of the terms in the basis are 1. Okay, can you see that the coefficients of on the left-hand side are all 1? Okay, so now there's nothing in an equation. There is nothing special about. There's really nothing special about left-hand side and right-hand side. The real focus is that I can write this, if I rearrange this statement, I could have written this statement as 1 times x plus 1 times y plus 1 times s plus 0 times t equals 5. Okay? That statement, just rearranging terms, I get this, and then I have 3 times x plus 2 times y plus 0 times s plus 1 times t equals 12. So there should be a 12 there. I can't write beyond that point, but can you see that should be 12? I'll just write it here. That's 12. Both equations are saying the same thing. There's only one key point that you have to keep in mind, is that look at these terms. S and T are the basic variables, so that's 5, that's not S, that's 5. S and T are basic variables, so you have a 1, 0, 0, 1 system, so that's a 0, okay? So associated with S and T, so in the first equation you have no T, in the second equation you have no S associated with it, and the coefficient of S and T are 1, okay? And you'll see this happen in the Tableau form, that we always, in the Tableau form, we'll be writing it in that form. In the algebraic form, it's easy to understand everything as let's express the non-basic in terms of basic, so that's why we are writing it as left-hand side, right-hand side here. Okay? Keep that in mind. All right, so if that were true, then this is what we have, and then we want to optimize 6x plus 5y. Your objective function should be like the constraints on the right-hand side, should contain the non-basic variables. Non-basic variables are x and y currently. There's no problem, so let's keep it that way. Then what? What is the objective value in this form that we have rewritten, which is basically the same form that we had, just rearranged terms. If I fixed x and y to 0, what's the objective function value? 0. So z equals 0, essentially what it's saying is in the first iteration of your algorithm, you're starting with the lowest possible values for x and y, yeah? Z equals 0. All right, so can we improve z? Every iteration you keep asking this question. At some point, you also will get, when you get to the optimal, you should be able to make a decision that we cannot improve z. That's where you stop. But at this stage, the question is, can we improve z? Now, what did I say x and y are? They are non-basic variables fixed to 0. Now, if I have to increase z, I have options of freeing up either x or y. x is fixed to 0. The only way to increase z now is to change one of x and y. Obvious? Otherwise I can't improve z. Now, I have two options. I can either improve x or I can improve y. Now, you already saw, I said that we are exploring a path to a different vertex connected to where you are. Right now you are at 0, 0. If in one direction you would go, you'll have to increase x. In another direction you go, you have to increase y. So which one would you choose? Anybody? Which one would you choose? Do you want to increase x or increase y? If I only gave you an option of increasing one of them. Anybody? Okay. Too early in the morning. So we can either increase x or you can increase y. Which one would you choose? Look at the coefficient of the term x and y in the objective. If I change x by 1 unit, you would get a 6 times increase in z because it's 6 times x. X is 0, x becomes 1, it grows, z equals 6. Y is fixed to 0. Let's assume that you fixed, this is incorrigible. Okay, so y is fixed to 0. If I increase x, there will be a certain rate of increase because the coefficient associated with x. On the other hand, if I fixed if I fixed x to 0 and if I increased y, that's what I meant. If you, in one case you are fixing one thing, increasing other, the coefficient of y is 5 and coefficient of x is 6 in the objective function. So increasing x gives me the steepest increase in the objective function. So I'll greedily choose a variable that gives me a steepest increase. Now, when I have to fix 1, we have decided that the coefficient of x is greater than the coefficient of y. So I'll choose to increase x and fix y to 0. What do I end up increasing? What do I end up increasing x to? Because right now x is 0. What do I increase it to? Now look at the constraints out here. Remember, if x was previously fixed to 0 and I'm increasing it, I need exactly some number of variables that are fixed to 0. In this case, 2. 2 variables have to be fixed to 0. X has been freed up. That means that I have to raise it, I have to change it so that one of the current variables that free becomes 0. Okay? So if I have to increase x here such that s becomes 0, so y is 0, so what do I increase x to so that according to that equation s becomes 0? Clearly 5, isn't it? If I change it to 5, 5 minus 5, s equals 0. So one potential thing is I can increase it to 5. Now see what happens if you substitute x equals 5 and y equals 0 in this equation. Do you get a feasible value for t? T would be negative, isn't it? If t is negative, clearly I can, by fixing s to 0, I'm exploring infeasible solutions, which I never want to do in this scheme of things. Which means that, well, okay, let's try the other option then. If I increased x according to the second equation such that t becomes 0 instead of s, how much do I have to increase x by so that t becomes 0? Clearly 4, isn't it? If I substituted 4, that becomes t equals 0. Now, if I substituted 4 here and 0, s is non-zero, it's non-basic, S is basic, it is non-zero, so it is a basic variable. S is not being fixed to zero, and it's feasible. So you had a choice of x going from 0 to 5 according to the first constraint, and 0 to 4 according to the second constraint. You always have to choose the minimum of the two so that both constraints are valid. Okay? You can raise it up to 5 and still be feasible according to 1. Raise it up to 4 and still be feasible according to 2. Which means that raising up to 4 will allow me to be feasible on both 1 and 2. So I want to explore the feasible regions, so I have to increase x to 4. And in doing so, original fixed variables or non-basic variables, non-basic, I'll call them NB, and free, basic, B. So original fixed variables were x and y. Original free was S and T. Now, I can free up x and fix t, because I'm making sure that t becomes 0. So t enters, becomes a non-basic variable, and x enters the basis, becomes a basic variable. Okay? So that's what the slides are going to tell you. In simplex, you only improve one variable at a time. I'm just going to go through. So if you have two choices, x and y. You're choosing a variable which gives you the maximum rate of increase in the objective function. 6 and 5 are the coefficients, so increasing x gives me the maximum rate, so I'll choose x. And I can choose x to 5 by the first constraint, but it gives me a non-negative, it flouts the non-negativity constraint in the second one. It doesn't satisfy the second constraint. So the other option would be to increase x to 4 according to the second constraint, and then you essentially, choosing the minimum of the two will give me a solution that is satisfiable by both constraints. And then, so if I did that, x enters the basis, t exits the basis, meaning that x becomes the basic variable and t is now fixed to 0, it is a non-basic variable. So what did we have to do? Rewrite everything in terms of the current basic variables on the left-hand side with coefficient 1, and the current non-basic variables on the right-hand side, whatever it takes when you transform. So you take the, and then so it's saying that the new basic variables are x and s. So x equals 4 and s equals 1 once you evaluate y equals 0 and s equals t equals 0 in the previous set of constraints. So what you have done is managed to go from here to a connected point right here. Okay, so that's what this madness is telling you, this method of madness is telling you. Now, I have to now rewrite, because t became, is basically exited the basis. Previously t was a basic variable. That's what t, everything was like that. I now have to rewrite it in terms of the current basic variable on the left hand side with a coefficient of 1 and the current non-basic variables on the right hand side. Non-basic variables right now are y and t. So if you look, if I transform this equation, I get this. Just stare at the equation, just see how I can get that equation. I just have to move things around, x to the left hand side, divide by 3, you essentially get that. Okay? Can you see that? Okay, now if you get that, I had a previous first constraint, because I started with the second constraint because x was increased such that the second constraint became 0. That's why I started with that. Now I have another constraint, the first constraint. So if I substitute this value out here, I end up getting that. Okay, it's just substitution of transformation of things, which ensures that what's the goal? I have to transform this whole system such that my coefficient of my basic variables, current basic variables in iterations are 1, and in algebraic form you have a tendency of writing them on the left hand side equal to the non-basic, some coefficients in terms of non-basic variables, which are y and t. So if you actually look at now the transformed form of both these things, you can see that y and t are the current non-basic variables. They are on the right hand side, right? So that's what you've done. The only thing that's remaining is to rewrite the objective function the same way. Previously the objective function was that, x was that. If you substitute that there, you end up getting the statement of the objective function with the current non-basic variables y and t on the right hand side. So all I have done is to follow the brief that everything should be expressed so that the non-basic variables are on the right hand side in the algebraic form. There's nothing special about left hand side and right hand side, it's just the coefficients that matter, but it's one way of thinking about this. Okay, so is everyone so far so good? So by the way, what did we say y and t were? They are non-basic variables. Evaluate z with y and z equals 0, y and t equals 0. It has to be 24 plus 0 minus 0, isn't it? That is 24. So you previously you had z equals 0, now you have a z equals 24. You've progressed up, you've moved the value up. So z equals 24 when y and t equals 0. Said, okay, now can we, so second iteration, same drill, rinse and repeat. Can we improve z? Can we improve z? So here's the objective function. Y has a coefficient of 1 and t has a coefficient of minus 2. Previously it was x and y with a coefficient of 6 and 5. We chose x because choosing x gave me the steepest increase. Now first things first, before we even pick one, if I have to increase z with y and t sitting at 0, obviously I can increase z by increasing y. That's obvious, right? So if t is 0, if y is being changed to 1, automatically the value would be z equals 24 plus 1, which is more than 24. If it's 2, 24 plus 2, it's obviously more. So increasing y helps. What about t? If I increase t from the fixed y to 0 and t, if I increase from t equals 0 to t equals 1, will I increase or decrease the objective function? 24 minus 2 is obviously going the other direction. So my only options are, if the sign of the coefficient is positive, increase. If the sign of the coefficient is negative, decrease. So I can decrease I can decrease t to increase the objective function, correct? So what is t currently? 0. Decreasing t gives me a negative value of t, isn't it? But what is the constraint on x, y, s and t? They have to be non-negative. So I really cannot explore infeasible solutions out here. So I will not even have to, out here I don't have a choice to do anything, change anything except y, because decreasing t is not feasible. Okay, that's what the next slide says, that decreasing t is infeasible. You only have to increase y. Now we can ask the same question, just going back one step. So if, think about this, y and t. So right now non-basic are y and t, basic are s and x, and if I have to increase y, t equals 0, according to the first constraint, how much do I have to increase y by so that x becomes 0? Everyone, please. So y equals 0, how much do I have to increase it by so that x becomes 0, according to this equation? So clearly, if y is increased to, let's say, 6, 2/3 times 6 is going to be 4, so 4 minus 4 is 0, right? So if I increase y to 6, fix y to 6 and fix t to 0, clearly x becomes 0, isn't it? X was not 0, it was basic. Now, if I substituted value of 6 here, t equals 0, would that be feasible? Well, it won't be feasible because 1 minus 1/3 of 6, it's 1 minus 2, which is minus 1. So I'm evaluating s equals minus 1, but we should not ever evaluate anything that is infeasible. So clearly that's not an option. So, okay, too bad. So what if I increase y according to second constraint and then make s equals 0? T is already fixed. So what do I increase it by? Y can be increased from 0 to 3, isn't it? If it's 0 to 3, I can evaluate it to 0. So clearly, it turns out that I had two options: increase y from 0 to 6 according to the first constraint and 0 to 3 according to the second, but this was infeasible, so I'm going to go with the second. Minimum of the two, always the minimum of the two, as we have done previously. Previously, we also chose the minimum of the two possibilities. So what you have here is choice of increasing y from 0 to 3. That's what we did. And then if you did that, my new basic variables are x and y, or y and x. So I'll write it original. Previously, you had non-basic, basic. You had y, was it y and t? Oh, sorry, y and t out here, and x and s out here. So now what you did was increase y, so it enters the basis, and you're making sure that s comes out. So s and t new, current is going to be s replaces y, and s and t are now fixed to 0, and x and y are in the basis, right? So if I have to write everything in terms of the current non-basic variables, which are s and t, I have to retransform. By the way, I must say that solution corresponds from, so previously we started here, we went here, out here. There's only one way to go in a connected path. You couldn't have gone here because it's infeasible, so you would have only gone one way up. So you came here. So if you did rearranged everything, the previous constraint, because s was a second constraint, which became s became 0, s became non-basic. You start with that, rearrange everything so that the coefficient of the new basic variable is 1. Okay, so basic variable is going to be y and x. So y and x on the left hand side, the current non-basic variables s and t on the right hand side. When you rearrange that, that's what you get. If you take this value of y and substitute it in the other constraint, you basically get the statement of x in terms of the current non-basic variables s and t. So we have done nothing more than just doing the same thing over and over again, but it's worth persisting. If this were true, we will still have to do one more thing, right? The objective function has to be stated in terms of s and t. Previously, it was in terms of y and t. So previously, the objective function was in terms of y and t, but we have this new set of things where y is 3 minus 3s plus t. That's what we saw in the previous slide. If you substituted that, you get this one. Now look at the objective function. I'll let you figure out why the transformations happen are correct. It's a simple rearrangement of terms really. But if you accept that the objective function is z equals 27 minus 3s minus t, if that were true, s and t are the current non-basic variables, so s and t are 0. What's the objective function value? It's 27, isn't it? Because s and t are 0. So we went from 0 to 24 to 27, so we are still progressing along. Okay, can we improve? So we kind of said objective function is 27, s and t are the new non-basic variables. Can we improve z further? We can keep asking every time, every iteration, can we improve z? Okay, where you are sitting at a vertex, looking to go to the next hop. Okay, now question is, look at the objective function, 27 minus 3s minus t, that's the objective function. What's the coefficient of s? Minus 3. Coefficient of t is minus 1. S and T are fixed to 0. For me to increase the objective function, I have to either decrease S or decrease T. S and T are currently 0. Is that even valid? You have to have non-negative constraint, right? If you decrease a value less than 0, it flouts the non-negativity constraint. So there's nothing I can do to the objective function that gives me a greater evaluation unless I'm willing to flout the conditions, which is not feasible. Hence, stop. At that stage, when you can no longer increase the objective function feasibly, you sort of say, well, there's nothing much I can do, stop. Okay? Well, that is a simplex method. Okay? Now I'm going to do how do I convert this into a algorithm? For me to convert into an algorithm, I have to be able to do a dry run of this on a paper. All right? On a paper, I should be able to solve this. And that's where the tabular form as a table form is important. Okay, so let's start with, I need a few colors. So the tabular form, I will go to the board now. You've got plenty of time, don't worry. So we are doing a tableau. I think French people, correct me if I'm, so T-A-B-L-E-A-U, I think, table form, if I misspelled it. I think X with an X is a plural and with a, yeah, something like that, okay? Table form of simplex. How do you do a table form of simplex? Okay, let's take the variables X, maybe I'll remove that for a moment. I need something on the top, space on the top. X, Y, S, T are the variables. Right hand side, that's R, H, S, right hand side. And theta, we'll figure out what this is in a moment. So I'm just going to draw a table. There are many different ways in which tabular form is written. This is how I internalized it, so that's how I learned. So online there will be slightly different variations of it. So now let's actually go back to the start of the, I'm going to have on the slide the algebraic form so that we can sort of see what's happening. Yeah, that's the start of it. So look at the coefficients of the objective function. The coefficients of the objective function are 6, 5, 0, 0. I'm going to call this thing J. So J equals 1, 2, maybe I'll write a different color there. Colors are important in this one. So see J equals 1, 2, 3, 4. There are only 4 variables here, so that's basically indexes. Okay, these are J is an index. Cj is that value, or that you're seeing there. So Cj is that value out here associated with index 4. Index 4, Cj is 0, index 3 is 0, index 2 is 5, index 1 is 6. You understand what this, it's an array of numbers. These are variables. So when you start, what did we do? We expressed everything in terms of the basic variables, isn't it? What are the basic variables? The basic variables are S and T when you started that equation. When you started the whole thing, X and Y were fixed to 0. So in terms of S, what is the coefficient? Look at the first constraint there. It is 1x, 1 times x, plus 1 times y, plus 1 times s, plus 0 times t equals 5. Can you see that equation there? Okay. Now, if I write in terms of the second one, 3 times x plus 2 times y plus 0 times s plus 1 times t equals 12. I've just, the terms, wherever that variable is missing. Now, remember, when you have, this is an iteration, whatever values you see against s and t in the Cj row, write it down here. I'll tell you what this even means. So write down whatever values of s and t. So let's call this s in the way that you normally see it. So s and t, whatever those coefficients you're writing out here. So what you're going to compute now is essentially what's called a Cj minus Zj value. Everything will fall in place once we keep looking at the algebraic version. So what is Cj? Cj, we said, is for 1, it is that term, for 2, it's that term, for 3, it's that term, for 4, it's that term. So we know what Cj is. So what is Zj? Zj for the first column is the dot product of these two terms and these two terms. So 0, 0, dot product, let's actually call it 0, 0, dot product with 1, 3. 0, 0 and 1, 3. If I do a dot product between those two, what is the dot product? Is basically the sum of component-wise products, right? So 1 times 0 plus 3 times 0. So that's what Zj would be. Z1 would be. Z2 would be whatever the term here, this times this plus this times this. Z3 would be this times this plus this times this, and so on, right? So let's do C1 minus Z1. C1 is 6, Z1 is 0, so it's 6. C2 minus Z2, C2 is 5, Z2 is a dot product between that vector and that vector. Basically, becomes 5. C3 is 0, dot product of 0 minus the dot product is 0. Similarly, C4 is 0, dot product is 0. Out here, you just do the Z value, only there's no C term out here. Z value is whatever the right hand side, dot product with this, 5 times 0 plus 12 times 0 is 0. Now, I'll show you what these numbers are in a bit. Now, actually, we can see it straight away. Can you see that this one is the statement of the objective function, 6x plus 5y plus 0s plus 0t with a z equals 0. That's what we evaluated in the first iteration, isn't it? The first very iteration, that's what we had. Now, if you did the second, just before we go to the second iteration, so that's what we had, we said, can we, so that's what we really had, the transformation of the objective function, where we said, can we improve z? So if you actually look at any of these equations out here, so s, rearrange them, you would see exactly these coefficients. So 1x plus 1y plus 1s plus 0t equals 5. 3x plus 2y plus 0s plus 1t equals 12. And then objective function 6x plus 5y plus 0s plus 0t equals 0. The value becomes 0 when x and y is equal to 0. Now, what did we say? Can we improve z? In this case, look at these terms and choose the largest positive value in that row, largest positive, right? So largest positive would be that. What is it corresponding to? It's corresponding to x, isn't it? So x is entering the basis, okay? Now we have to figure out which leaves. To do that, when you pick this column, you've selected this column, look at the right hand side. If you divide the corresponding terms, 5 divided by 1, and then 12 divided by 3, 5 divided by 1 is 5, 12 divided by 3 is 4. What are these possibilities? Those possibilities were the last two. So 5, you can increase 5 or increase 4. It'll tell you how much you could increase it by. All I have done is whatever variable that's entering that column, right hand side divided by the corresponding term in the column. Essentially, what it's capturing is the logic, what we explained, into some set of instructions, which is what an algorithm is. Do this, do this, do this. It's a stepwise statement of an algorithm. So if you did that, so you have chosen the largest positive, you have to now choose the smallest positive out here to leave. So what is this? This is associated with the row T. So X is entering, T is leaving. Okay? Now that's basically going to be the intersection between the row the column that's the variable of the column that's entering and the row that's leaving. So if that happens, then clearly the new basic variables are S and X, isn't it? In place of T, I have X now. Okay? I'll just create more space here. S and T. I'm just going to write it a bit compactly because I have a few more iterations to go. Okay? Now, the moment you have the new variables, can you please look at what are the Cj values here? Well, the Cj value of S is still 0. What's the Cj value of, this is X, I must say. This is X, not T is being replaced by X, isn't it? Okay? T is going out and X is coming in. So the Cj associated with S is 0. The Cj associated with X is 6. So now previously you had 0, 0. Now you had 0 and 6. Now let's continue. Now, how do I get these rows? Well, first start with the second row, the intersection of those two things. So can you see a number here that's basically 3? That's the intersection of the row and column. Divide everything by that number. So that's going to be 3 divided by 3 is 1. 2 divided by 3 is 2/3. 0 divided by 3 is 0. 1 divided by 3 is 1/3. 12 divided by 3 is 4. Okay? Can you see that? Now, how do I get this row? Well, I get this row by taking the old S, okay, taking the old S and the new X. What is the transformation? What are the row operations that I should do with the old S and the new X so that I can get a new S? So what are the row operations? What are my fixed points? What are the basic variables here? S and X, which means that you would have 0 out here. I should get a 0 out here and a 1 out here, because always the coefficient of, in each constraint, the coefficient of each basic variable is going to be 1. And the other will be missing in that constraint. So I have to do a row operations between those two so that I get a 0 here and a 1 here. You can very clearly see that if I subtract this, the old S with the new X, 1 minus 1 is 0. And out here, 1 minus 0 is 1. So that kind of gives me a simple subtraction of this minus this. So 1 minus 1 is 0. 1 minus 2/3. 1 minus 2/3 is 1/3. 1 minus 0 is 1. That's what we wanted. 0 minus 1/3 is minus 1/3. 5 minus 4 is 1. Okay? So I basically have that statement. Now, what is that? Okay, but before we show these, the equivalence, Cj minus Zj. What is Cj minus Zj out here? Cj, 6. C1 is 6. Zj is the dot product. So dot product is 0 plus 6. So 6 minus 6 is 0. Cj minus Zj. So Zj is 6. Cj is 6. Cj minus Zj is 0. So Cj minus Zj, Cj is 5. Zj is, that's 0 plus 6 times 2/3. So that's going to be 4. So 5 minus 4 is 1. I'm only doing Cj minus Zj. Cj is 3. Cj for column 3 is 0. Zj is the dot product. Dot product is 1 times 0 plus 0 times 6. 1 times 0 is 0. 0 times 6 is 0. So Cj is 0. So that's going to be 0. And then Cj minus Zj out here. Cj is 0. Zj is 0 times minus 1/3 is 0. and then 6 times 1/3 is 2. Okay, so that's going to be minus 2. By the way, what is z here? Z is nothing but the dot product. What's the dot product? Is 24. The objective function jumped from 0 to 24. And why, what are all these numbers? I will just quickly go to the part where we had the terms there. Can you please stare at the coefficients in each of the equations? So for x, 1 times x, okay, 1 times x, can you see that? 1 times x, first constraint, plus 2/3 times y. If I moved minus 2/3 times y to the left hand side, I'll get plus 2/3 times y. So that's 2/3 times y plus 0 times t. If I moved minus 1/3 on the right hand side to the left hand side, it would be plus 1/3 times t. So sorry, 0 times s plus 1/3 times t equals 4. That's the first constraint. The second constraint is, if I move 0 times x, there's no x in the second one, 0 times x plus 1/3 times y plus 1 times s minus 1/3 times t. If you kind of rearrange the terms. Can you see that, everyone? It's basically the same things that I'm written in the tabular form. And what is the z value? It's basically, if you look at the terms there, there's no x term, so 0 times x, there's 1 times y, 0 times t, there's no, so 0 times s minus 2 times t equals 24. That's what you have here. Okay? Can you see the equivalence between the two? Okay? So if you have this, what did we have to do? Choose the largest positive number in the Cj minus Zj. Largest positive is this. So what is this corresponding to? The column y, isn't it? So column y, so y enters. Now we have to figure out which leaves. So to figure out which leaves, divide the right hand side by the corresponding term in that column that's entering. So 1 divided by 1/3 would be nothing but 3. That's what theta is. 4 divided by 2/3. So 4 divided by 2/3. 4 into divides by 2. So 2 times 3 is 6, isn't it? So 4 divided by 2/3 is nothing but 6. Okay? So you essentially have 3 and 6. Now those numbers should be familiar. So we remember we chose 3, but there was also a 6 as a possibility, and there are two possibilities: increase y from 0 to 6 or y from 0 to 3, and we chose the minimum of the two. So we have to choose a minimum positive in theta to leave. So that corresponds to that term there. So S leaves. So t leaves here, and t leaves. X enters, y enters. So now out here, y is entering and S is leaving. So what would be if y enters and x leaves, I'm going to get y and x as my new basic variables. I don't need more space than that. So if I have to now rewrite the equations in terms of the new basic variables y and t, y entered, s left, which means that the intersection of that is that term, 1/3. If I divide this row by 1/3, I get the notion of y. That's what will happen. So 0, 1, so 0 divided by 1/3, 1/3 divided by 1/3, that's the intersection of the columns that are entering and leaving. So 1 divided by 1/3 minus 1/3 divided by 1/3, 1 divided by 1/3, which is basically 3, isn't it? So that's what I got. So 0 divided by 1/3, 1/3 divided by 1/3 is 1, 1 divided by 1/3 is 3, minus 1/3 divided by 1/3 is minus 1, 1 divided by 1/3 is 3. Now I have to find my new x from my old x and my new y, those two rows. Now what are the fixed points? I know that because x and y are in my basis, these coefficients have to be 1 after I do the row operation, right? Because you only have one of each in any constraint. If there is nothing here, there has to be 1. If there's one of this, there's nothing out here. So what can I do to these two rows so that I can get a 1 and 0 out here? Okay? Can I simply subtract? Well, it looks promising initially. If I subtracted, it looks promising initially, but there's a problem later. Let's see if I did a plain subtraction like we did the previous iteration. 1 minus 0 is 1. Well, that looks promising. But then 2/3 minus 1 is not 0. So that doesn't help. So what can I do? Anybody? To the row operation so that I can get a 1 and a 0? What if I multiplied this by 2/3? If I multiplied this by 2/3, okay? If I multiplied this, so x minus 2/3 of y. So x, if I did x old minus 2/3 of y new. Okay, that's y new. This is x old in the sense that the previous iteration. If I did that, 1 minus 2/3, so 1 minus 2/3 of 0 is 1. 2/3 minus 2/3 of 1 is 0. 0 minus 2/3 of 3 is minus 2. 1/3 minus of minus. So minus 1 times 2/3. Minus of minus is plus. So 1/3 plus 2/3 is 1. And then 4 times. So all I have done is I have taken this and subtracted with 2/3 of that term. So 1/3 minus of minus 2/3. So 1 plus 2/3. 1/3 plus 2/3 is 1. Similarly, 4 minus 2/3 of this is going to be 2. Now, by the way, x and y are out here. Remember, we needed to write the Cj values, those green values out here. So y is nothing but 5 and this out here. So now we can ready to compute Cj minus Zj. What is Cj? C1 is 6. Zj is the dot product of that vector and that vector. 0 Zj for this thing is 0 times 5 is 0 plus 6 times 1 is 6. So Cj minus Zj is 6 minus 6 is 0. Cj minus Zj, 5 minus 5 times 1 plus 6 times 0, 5 minus 5 is 0. Cj minus Zj, 0 minus 15, okay, this is not a minus, a 15 minus, so 15 minus 12, dot product 15 minus 12, right? 15 minus 12. 15 minus 12 is what? 3. Cj minus Zj, Cj is 0, minus 3 is minus 3. Similarly, Cj minus Zj, 0 minus Zj would be dot product 5 times minus 1 is minus 5 plus 6 times 1 is 6. So 6 minus 5, so 5 times minus 1 is minus 5, 6 times 1 is 6, so 6 minus 5 is 1, dot product is 1, Cj is 0, Cj minus Zj is minus 1. And what's the Z value? The optimal, the value that we have to evaluate, it's just the dot product of that and that. So 5 times 3 is 15, 6 times 2 is 12, 15 plus 12 is 27. So you went from 0 to 27, 24 to 27, right? We increase the value. Then next iteration, we can stop straight away, but next iteration, can we increase Z? Well, find me the largest positive value in Cj minus Zj. Do you see any number that's positive? 0, but not positive. So the moment you get such a thing, you get stop. If you stop there, look at the value of x and y on the right hand side. X equals 2, y equals 3 is your solution to the problem, it turns out. By the way, works for any number of variables. Now, when you're writing a program, essentially you have to load the system with certain number of a structure of what the iteration would be, coefficients would be, and then you always can choose. The method is the steps are very clear. You can compute Cj minus Zj, choose is there a positive value, the answer is no, stop, otherwise okay, pick the positive value, find theta, exactly what minimum of the values in theta, and then rearrange the equations with row operations, repeat the process. So it's basically a simple method of iteration. And by the way, that value, I just wanted to say that if you actually saw the terms here, so if you actually saw everything in the last part, last iteration, stare at the coefficients. So if you look at y, okay, so if you look at the second one, 3 is on the right hand side, coefficient of x in the second constraint is 0, coefficient of y is 1, coefficient of s is 3 if you moved it onto the left hand side, can you see that? And then coefficient of t is going to be minus 1 according to the second equation if you moved t on the left hand side. Similarly, coefficient of x is 1 according to the first constraint, y is 0. According to the first constraint, if you move 2s to the left hand side, you get minus 2s, so coefficient is minus 2. If you moved minus 1t to the left hand side, you get plus 1t, so that's going to be plus 1, and that's going to be right hand side is 2. And then objective function is 0, 0, minus 3, minus 1, and that's 27. So everything that we did was algebraic form, just giving you a method of crank turning. That's voila. Nothing more than that. I just wanted to say perhaps, so the slides will give you everything that I did on the thing. So we'll just quickly check if the last numbers are correct. Okay, so 0, 0, minus 3, minus 1, that seems, I didn't make any computational errors while talking. Yep, that seems reasonable. So you stop. And I gave you a link of how to change. This is non-examinable. Don't worry about non-standard form. Even if you understood the standard form, it is a great progress in my view. Might not be yours, but my view, because I feel that there are certain algorithms that are classics. Simplex is a classic. Why is have you ever realized why dynamic programming is called dynamic programming? There's nothing dynamic about it. It's because it came after linear programming, and they really wanted to have this notion of differentiating, of solving an optimization problem with linear ordering constraint, which followed what's called a Bellman's conditioning. So that's Bellman condition of optimality. So the importance of linear programming is such that even problem-solving strategies were named sort of to distinguish itself from that thing. So it's from the what I believe is a very important algorithm in the literature. Now, there's a whole world of combinatorial optimization, primal dual algorithms, and that opens up. So next week, I'm going to talk about something which is an extension to your learning from your network flows problem, okay? But also it is an extension to, this is a standard simplex. So what do you mean by doing a dual simplex? So it's a different version of a dual simplex problem. You would have done a dual simplex problem in terms of Ford-Fulkerson's algorithm, min-cut max flow. The two versions are the primal and dual versions of the problem. So one's a dual version and then the primal version. We'll see what that even means. But there's a whole class of optimization research. If you're doing graduate level courses, these days you could do graduate level courses or even perhaps PhDs without knowing it. Everything is an import something in Python. But I think if you applied yourself, it is very intellectually extremely satisfying. It opens you up with notions of how do you programming with linear constraints, and perhaps in graduate level you'll also explore how do you program with non-linear constraints. So convex programming. What is quadratic programming, for instance? What are KKT conditions? And there's a whole sense of literature which I was really fascinated in my own journey, that for those who want to do read ahead, this is like a small door that it opens for you. You won't go there fully blind. You will at least see that there's this method that is real world, very powerful, gets used almost on a daily basis in logistics in some varied forms. So it gives you that window of getting into a new world. Okay, that's it. Thank you. I'm sorry I got a bit late, and next time I'll make sure that I at least take off a few more minutes to account for traffic. I think I started about 5 minutes late, if I'm not mistaken, but yeah, really apologize though. I wasn't stressed because this lecture would not have taken longer. All right. Any questions? I'll be outside if you want to ask me any. All yours.
I get 2 to my class, plus a tutor.
Oh, I got 3 then.
Yeah. How big is your class?
300.
Oh, okay, I got 240.
And mine's starts at 8, so.
Oh, right. Yeah.
So
Is it
does
a core unit?
It is in computer science.
Mine's an elective.
Yeah. I think.
We're all changing.
Yeah. Well.
We've got to change, I think. Yeah.
So you're going to a recording, is it?
No, you're going to do a bit of recording, and then it's a workshop thing. But you've got 2 people doing it.
Okay. All right. Fair enough.
I think you have your mic on.
Oh, sorry. I was stealing your mic, it turns out.